So, in the last class we have discussed the, if there is a random process x of t while stationary ergodic and given Rxx tau, how do we expand this in terms of an orthonormal series whose coefficients of this orthonormal series will be in the uncorrelated, right? Every expansion will not give you uncorrelated. For example, you are all familiar with making sampling. So, if you do sampling on this, theoretically it should be okay. Omega alpha it also has a finite bandwidth, the spectrum of that has a finite bandwidth. So, we can also sample like the deterministic signal. But unfortunately, what happens is that most of the cases the samples are not uncorrelated. Unless the sampling distance between the one sample to other sample is extremely large. And we may not be able to sample such a short long distance because then you will not get the proper samples. So, what is that expansion which will give you the coefficients which are uncorrelated? We found in the last class that the requirement is that it should satisfy, I don't know what, yes, integral minus infinity to plus infinity Rxx tau minus alpha into h into phi k alpha d alpha must be equal to some lambda right. That means the time function here satisfies this integral equation, and there must be methods of solving that integral equation. I will just take a very cooked up example of some process x of t whose Rxx tau happens to be a square by 2 cosine omega 0 tau. In the sense that I am not telling you what is that process which will give you this as the correlation function, but I will do the solution to this equation and come up with what is the expansion for x of t, and it turns out to be that process which gave rise to this. Right now, I will not tell you what is that process. So, let me write down this integral 0 to t naught because it is a periodic process. So, I expand it only for a one period 0 to t, and t0 is equal to twice pi by omega naught. First. F is equal to 1 by t naught. Okay. So, I will write down this integral equation 0 to t0 a square by 2 cosine omega 0 t minus alpha phi n t right. This expansion is varied between 0 to t naught. I need a solution for this. So, let us do this. It is very simple to solve. So, I have taken this example. Expand this. Right? So just substitute that. This can be written down as equal to 0 to t. I can pull this out because it is independent of integral. Right. Same thing I am writing for the first part of it. This one. I do similar thing for the second part later on. First, let us take this. Now, if phi and t is equal to cosine omega naught k times t, some k is an integer. Now, just you can look at it and see that if this phi and t happens to be this, and then this will satisfy this equation. Yes or no? If this is a solution to this will satisfy this equation. Lambda n is lambda n and k is equal to 0. I am sorry, this is k. You are not seeing the point. This is the equation that is to be solved. Is there, what is the solution for phi and t which will satisfy this? One thing we know that cosine omega alpha and any multiple of that will be integral from a for one period will be equal to 0. And when cosine omega t alpha t is multiplied by another cosine omega alpha t, then obviously this will have some value with me. So, this equation is satisfied by a relation phi k t or phi n t is equal to cosine n omega naught t. In that case, L alpha n is equal to 0. It satisfies that. Only thing is, if phi and t is equal to cosine omega naught t, then this equation will give rise to a value equal to half cos square expanded half something. The second harmonic will be average to 0. So, we will get a half here, and half a square by 2 cosine omega t is equal to lambda n, again cosine omega t. So, satisfied. So, one solution to this problem is that phi and t is equal to cosine n omega naught t for n not equal to 1, in which case the corresponding lambda n is equal to 0. Other solution is phi and t is equal to cosine omega naught t if n is equal to 0, n is equal to 1, for n is equal to 1, in which case lambda n is equal to a square by what? 4, right?